Good morning. Today I'd like to begin our discussion of Chapter 12. So Chapter 12 is going to be a continuation of what we started in Chapter 11, looking at the three different phases of matter. So in Chapter 11, we focused on the properties of gases and aspects of how gases behave. And in Chapter 12, we'll do the same, but we'll be looking at liquids and solids. Now, one of the things that we stressed about gases, right, is that gases, they operate under the kinetic molecular theory. And one of the big tenets under there is that there is a lot of empty space and the particles of gas are not attracted to each other. Now, that's true of gases for the most part, at least under normal sort of conditions. But this is absolutely not true for solids and liquids. And the way we describe that is with the existence of something called intermolecular forces, right? So this is what holds the molecules of a liquid and solid together, right? So this is what attracts those molecules. This is why liquids exist as drops or large groupings of molecules, right? And so, while gases have lack of intermolecular forces, have very little to no intermolecular forces, and therefore are free to expand to fill their container and have lots of empty space in between and collide and bounce off each other, right? Solids and liquids do not have all of those same freedoms because of the presence of these intermolecular forces, these attractive forces that exist among liquid and solid molecules. And the specific types of these interactions, right, we'll look at a little bit later in the chapter. But these interactions are responsible for a host of interactions, right? Lots and lots of things that we think about in nature. Just to give a couple examples, taste receptors in the mouth, right, you have molecules that come in, they attach by these intermolecular forces to these receptors, and they give us taste. We'll learn earlier about the fundamental, building block of our body's DNA, right, that are responsible for all of our characteristics, are heavily reliant on intermolecular force for their existence, right? And so these forces are extremely important, and in fact, they are responsible for the very existence of liquids and solids, right? So as we move on, let's look at some of the ideas that we've talked about in previous chapters associated with molecules. So we know that the molecules and atoms that compose matter are in constant motion, right? And as the speed of this motion increases, right, we get temperature increases, right? So a sample at higher temperature means that the molecules are moving faster, right? Remember, temperature is the average kinetic energy of the atoms or molecules in a sample. And we call this, remember, the thermal energy of a sample. And so this can all be tied back to intermolecular forces, right? And so if a species or a compound has weaker intermolecular forces, right, then the samples will tend to be gaseous at lower temperatures, right? Or because as the molecules start moving faster and faster, those weak intermolecular forces will break and the material will exist as a gas. And if those forces are weak enough that they break below sort of normal temperatures, right, what we think about as sort of room temperature, then those species will be a gas at room temperature. Right? So materials that have weak intermolecular forces will tend to be gases. Molecules that have stronger intermolecular forces will tend to be liquids and solids. Now, of course, we're going to focus on liquids and solids when we talk about intermolecular forces because those are the species that actually have intermolecular forces at sort of normal conditions. But now, just to sort of refresh our memory about some of the basic differences, fundamental properties of the three phases, we can look at this table, right? And we've talked about some of these in the past, right? We've talked about the relative density of the gas and liquids and solids. We've talked about how gases have undefined shape and volume due to their lack of intermolecular forces. And liquids have defined volumes because of the presence of intermolecular forces, right? Now, the strength of these, the moderate intermolecular forces that exist in a liquid, allow them to have some additional motion, which allows for the shape to change for things like flow and pouring and some movement, whereas solids are essentially locked into place, right? They have a definite shape and a definite volume. And so all of these sort of ideas get tied back to the strength of the intermolecular forces within these liquids and solids. Now, we'll remind ourselves that there can be two kinds of solids, crystalline and amorphous, and we'll reference back to crystalline solids at the very end of the chapter when we sort of define different types of crystalline solids. So we're going to close out this first video by looking at a couple of properties of liquids that can directly be tied to the presence of these intermolecular forces. And these are surface tension and viscosity. So, while the most important manifestation of these intermolecular forces is the fact that solids and liquids exist at all, right? Without them, everything would be a gas. And so that's the most important. But a couple of these other important concepts, again, are what we call surface tension and viscosity. So surface tension is this idea that liquids will tend to minimize their surface area. Right? So they will adopt a shape that will give them the smallest amount of surface for the maximum amount of volume, if you will. Now, we can sort of envision this in a few ways, right? If you take a sample of liquid and you really lightly touch your finger to it, right, like right here, you can, if you're really careful, you can see yourself making a little dent in the water without actually going in to the surface of the water or without actually going into the bulk of the water. The surface tension acts like a skin, if you will, on the surface. And so you can get a paper clip to float on the surface of water, and that is, it's floating and it's not sinking because it's not breaking the surface tension. So the surface tension is this force on the top of the water that sort of creates a barrier that you need to apply a minimum amount of force to break through that surface. So why do we have surface tension? Well, if we look over here, we can see that at the surface, right, the molecules are not evenly surrounded, right? There's a part of that do not have any intermolecular forces, right? Because it's the surface. And so because of this imbalance, right, that there's what we might think about as unequal pulling and it pulls the molecules a little tighter together. If we look at an interior molecule where it's attracted on all sides equally, right, there is more space, right? They're pulled equally. And here, the surface, these are being pulled downward and across more, and it creates tighter, closer spacing of the molecules at the surface, and it creates this skin, if you will, this barrier at the surface, which prevents things from sinking unless they apply a minimal amount of force. Now, that force is not great, right? It's easy to break the surface of water, and in fact, if you take a paper clip like this and just touch it, right, you can typically get it to crack the surface, and then once it does, it sinks straight to the bottom. Now, different materials will have different amounts of surface tension based on their intermolecular forces, right? So water has reasonably strong intermolecular forces for a liquid, and therefore has a relatively high surface tension, whereas gasoline has a really low surface tension because it has weaker intermolecular forces. So you'll never be able to get a paper clip like this to float on gasoline because the surface tension is too weak. So this is surface tension, one of the manifestations we see of intermolecular forces in liquids. And one more, and that is what we call viscosity. So viscosity is the resistance to flow of a liquid, right? So we think about liquids flowing, but there is a resistance to this flow. So some things flow more slowly than others because of this higher viscosity. And again, part of that viscosity is due to intermolecular forces, right? So if we have a high viscous, they flow more slowly than low viscous liquids. So as an example, motor oil is relatively viscous, whereas gasoline has a lower viscosity, right? Pours more easily, right? We think of these as sort of thick, and these as not so thick. Maple syrup, right? More viscous than water. Now, the viscosity is going to be higher in liquids that have a stronger intermolecular force because the molecules can't move around each other as freely, right? If we think about the molecules that are moving past one in each other, they're going to stick to each other more if there's higher intermolecular forces. It's going to be harder for those molecules to break free from each other and slide around, which is what we get when we pour things, right? The molecules are sliding past one another, which is why we see the flow. So intermolecular forces are partly responsible for this. Now, there are other things that lead to high viscosity, and that is the shape of molecules. So if we have long and skinny molecules, such as really long hydrocarbons like oil, right? And the molecules that are in maple syrup, right? These molecules will tend to become entangled, just simply like hair becomes entangled. They tend to wrap around each other and they get stuck on each other. And that entanglement causes a slow flow or a higher viscosity as these molecules get tangled up with each other. So, viscosity, another property of liquids that has some relationship to the strength of intermolecular forces in that liquid.